Ladies and gentlemen, first of all, I would like to thank Dr. Takashi Ono, Chairman of 9th IOC, for this speaking opportunity at APOS. My name is Noriyoshi Shimizu. I'm from Department of Orthodontics, Nihon University School of Dentistry in Tokyo, Japan. The title of this presentation is Easy Debonding of Ceramic Brackets Bonded with a Light-Cured Orthodontic Adhesive containing heat-expandable microcapsules with a CO2 laser. In recent years, research on dental adhesive resins has progressed, and the bond strength of orthodontic adhesive has become very strong. On the other hand, the increased bond strength makes it difficult to remove the bracket after treatment and often causes some problems. Then, an orthodontic bracket adhesive is required to have the contradictory properties that family bonding of the bracket to the tooth surface during treatment and easy removal of the bracket after treatment. After orthodontic treatment, a strong load must be applied to physically remove the brackets. At this time, strong toothache, enamel cracks, and bracket breakage often occur. Therefore, it is ideal for the orthodontic adhesive to have both properties of family bonding of the bracket to the tooth surface during treatment and easy removal of the bracket after treatment. For this purpose, it is necessary to take measures to reduce the bond strength. We started to study adhesive that could easily remove the bracket after treatment, and we focused on the heat expander microcapsules, as shown in the slide. The size of the microcapsules is 10 to 20 micrometers, and they expand 70 times larger when heated to 80 degrees Celsius. At first, we examined a prototype for meta-MMA TBB resin adhesive, which is chemically polymerized orthodontic adhesive, and the product name is Super Bond, containing a certain amount of the microcapsules. We reported when the bracket bonded with this prototype adhesive was heated with a 300-degree heater, the bond strength decreased to 0.4 times before heating using metal brackets. We also reported similar results using the ceramic brackets as shown in the papers. However, considering the clinical application, it is necessary to find a safer heating method, because a 300-degree heater may cause burns of surrounding soft tissues. In recent years, dental lasers have become widespread and many clinics have various laser devices. Among them, the CO2 laser has the advantage. Especially, it has a wavelength most easily absorbed by the ceramic bracket and has a heating effect. When a similar experiment was conducted using CO2 laser irradiation instead of a heater on a ceramic bracket bonded with a super bond containing microcapsules, the bond strength was significantly reduced by 0.3 times. It means the laser irradiation was effective to expand the microcapsules by heating. Light-cured adhesive has been widely used in recent years because brackets are easy to position and many brackets can be bonded at once. Therefore, a similar study was conducted using this GMA light-cured adhesive. The product name is Transbond XT. At first, a preliminary experiment was conducted by mixing microcapsules in the resin paste of Transbond XT, as shown on the left. But there was no decrease in bond strength by laser irradiation. Therefore, The next experiment was conducted by mixing microcapsules in the resin primer instead of the paste, as shown on the right. The bond strength of ceramic bracket was significantly decreased by the laser irradiation. Then, a detailed study was conducted under these conditions. The purpose of this study was to examine a method to remove the ceramic bracket safely and easily by irradiating CO2 laser to the bracket bonded with the light-cured orthodontic adhesive in which the heat-expandable microcapsules are mixed in the primer. The outline of the experiment is setting of CO2 laser irradiation conditions, measurement of shear bond strength of bonded brackets, assessment of residual adhesive. In this study, Yoshida's Operator Pro is used as a CO2 laser device. Its wavelength is 10.6 micrometers, continuous wave, and irradiation output is 5 and 7 watts. In order to set the appropriate CO2 laser irradiation conditions, the temperature rise in the bracket base was measured with our K-type thermocapsule sensors in contact with the bracket base when the laser irradiation was performed. The temperature increase in the pulp chamber was also examined when the bracket base temperature rises above 80 degrees. A ceramic bracket was bonded to the buccal surface of the human premolar, which was removed for orthodontic treatment using light-cured adhesive, and a hole was opened from the cement enamel junction on the lingual side. A K-type thermocapsule sensor was positioned on the inner wall of the pulp chamber corresponding to the surface where the bracket was bonded. The measurement of the temperature in the pulp chamber was performed at room temperature of 23 ±1 degrees. The preparation of bovine tooth specimens and bracket bonding. The cat bovine lower mandibular incisor crown was embedded in a resin, and the polished labial surface was etched with 37% phosphoric acid etching solution, as instructed by the manufacturer, washed with water and dried. The tooth surface was coated with light-cured adhesive primer containing microcapsules, and the bracket was bonded with Transbond XT resin and light irradiation for 20 seconds. The sample after bonding, the bracket was immersed in distilled water and 37 degrees for 24 hours. The shear bond strength of laser irradiation and non-irradiation groups was measured 10 minutes after irradiation using a universal testing machine. After measuring the shear bond strength, each sample was observed with a stereoscopic microscope at 15 times magnification to identify the fracture mode of the bond surface. The ARI score is determined 0 to 3, as shown in the slide. The results are as follows. The bracket base temperature was measured during irradiation in 5 watts for 3 to 6 seconds irradiation, as shown in the slide. The maximum temperature did not reach 80 degrees regardless of the presence or absence of air cooling. With 7 watts irradiation, the maximum temperature reached 80 degrees or higher after irradiation for 5 and 6 seconds with or without air cooling. Therefore, the both irradiation time were considered to be appropriate. Temperature increase in the pulp chamber after irradiation of 7 watts for 5 and 6 seconds was also measured. Zhang and Cohen reported that the temperature increase in the pulp chamber of 5.5 degrees or higher may cause damage due to thermal degeneration of the pulp. Among the various conditions, the temperature increase in the pulp chamber was 5.36 degrees on average, only when irradiated with 7 watts for 5 seconds with air cooling. Therefore, the subsequent experiment was performed under this condition. The results of the shear bond strength of the irradiation and non-irradiation groups are shown. The blue column is the non-irradiation and the yellow column is the irradiation group. It is reported that the red dot line with a bond strength of 9.7 MPa may cause enamel crack when removing brackets, and the purple band of 6 to 8 MPa is suitable for orthodontic treatment. In the group containing 0, 10, and 30 weight percent microcapsules, no significant difference was observed. However, in the groups containing 20 and 25 weight percent, the shear bond strength decreased significantly in the laser irradiated group, which was 0.39 and 0.17 times compared to those in the non-irradiated group. In this study, a light-cured adhesive with a microcapsule content of 25 weight percent had suitable bond strength for orthodontic treatment, and irradiation with a CO2 laser for 5 seconds significantly reduced the bond strength. In the evaluation of ARI score, there was no significant difference between the laser irradiation and the non-irradiation groups in the groups containing 0 to 30 weight percent of microcapsules. As an additional experiment, 7 watts for 5 seconds laser irradiation rises the pulp chamber temperature to near the degeneration temperature, thus risking pulp damage. Therefore, when the bracket base temperature reached 80 degrees by laser irradiation, it was 8 seconds after irradiation. A cold water was dripped onto the bracket, and then the temperature rise in the pulp chamber was significantly suppressed to 3.1 degrees. The water cooling method is a safer method for protecting the pulp. The bracket removal method by heating and softening the adhesive by laser irradiation has been reported. But this operation is very dangerous because the softened adhesive is so hot. Furthermore, the reduced bond strength recovered in 18 seconds. In this study, the bond strength using microcapsules does not recover once expanded. Then, many brackets can be safely removed at one time with a light force after cooling. The bond strength of the ceramic bracket using a light-cured adhesive primer containing 25 weight percent microcapsules was strong enough to withstand orthodontic treatment, and the bond strength was significantly reduced, which was 0.17 times less than that before by CO2 laser irradiation for 5 seconds. After 5 seconds of laser irradiation, the temperature of pulp chamber rose 5.36 degrees, which is close to the temperature that damages the pulp, but it can be suppressed to 3.1 degrees by water cooling. In conclusion, it is most likely that the bracket removal method using CO2 laser irradiation on a ceramic bracket bonded with a light-cured orthodontic adhesive containing 25 weight percent of microcapsules can reduce toothache, enamel cracks, and bracket damage. and also shortens the removal time. Thank you for your attention.